Hey guys, Dr. Butts here coming with a fantastic chemistry video, and today we're going to start talking about representations of molecules and Newman projections. Let's get right after it. Methane representations. Now here we have three different ways that we represent organic molecules. Now this is something that you're already familiar with because we've already talked a little bit about it in class. It is the wedge and dash version of the tetrahedral. As we discussed in class, these three atoms are coplanar. This wedge means the hydrogen is coming out towards you, and the dashed line means the hydrogen is going away from you. Now this is what they call a ball and stick model. The ball and stick model has the methane, has a hydrogen coming towards you, hydrogen going away from you, and these hydrogens are coplanar. This is known as a space filling model. These are basically the electron clouds of the atoms that are attached to the black carbon in the center. All right? And these are just different ways we represent molecules. Now this by far is the most common way you'll see them. But sometimes space filling models and even ball and stick have their place. So here is an ethane molecule. Here's a ball and stick of an ethane. Here's a wedge and dash of an ethane. Notice you have the hydrogen here in the plane, this carbon, and then this hydrogen are all in the plane in that little zigzag type pattern that I showed you before. Hydrogen out, hydrogen out, hydrogen down, hydrogen down. And here's the ball and stick representation, and here's the space filling model. Now remember, this carbon-carbon single bond, this one right here, can freely rotate. So now we're going to see the ramifications of that, and that's conformations. Conformations are different arrangements of atoms caused by rotation about a single bond. Oops, it's not on page here. There we go. Try that again. Different arrangements of atoms caused by rotation about a single bond. That's conformations. So let's see what happens when we change the conformation of ethane. So now, take special note of where this hydrogen is and where this hydrogen is. Okay? If we rotate about the single bond, leave this one where it is, leave this one exactly where it is, and we rotate this methyl group backwards a little bit. So we're going to start here and pull it forward, or pull it around, excuse me. Notice what happens. This hydrogen that was now in the plane is now here. This hydrogen that was here rotates to, believe it or not, right here. Let me put some numbers on here. Hydrogen A, hydrogen B, hydrogen C. Hydrogen A, hydrogen B, hydrogen C. Believe it or not, that's where they ended up. And that's simply because of rotation about the bond. So let's label them here. A, B, and C. A, B, and C. And that's simply due to rotation about the double bond. That's all that's causing this. Okay? Now, obviously, this is pretty interesting. All right. Now, pure conformations cannot be isolated because they're happening too fast and there's just no way to stop it. So they cannot be isolated because the molecules are constantly rotating all the time. They're always moving. All right. Now, these things or these phenomena or these conformations are generally depicted using what's called a Newman projection. Okay. And here's how you draw them. First of all, we're going to take it from the perspective of this bond right here. Okay? So we're looking straight into this carbon, straight into this bond. So now, the way you draw a Newman projection, start out with just a simple circle. They all start that way. Every Newman projection you're going to draw from now and until you're done with chemistry, you draw a nice big circle. And then draw three lines like this, a V, and then straight up like that. Okay? Now, what's attached to those lines? Well, first of all, you have to understand that this carbon right here, there's a carbon right there, that's the front carbon. That's the carbon that's right here. Okay? And from this point of view, if you look straight up from this point of view, what do you see? Well, you're going to see this hydrogen right here, right? If you look down from this point, if you look down from this point of view, you're going to see this hydrogen to your right and this hydrogen is to your left if you're standing here. If you're standing here, this hydrogen is down to the right, this one is down to the left. Okay? And there you go. Let's give them a quick label. A, B, and C. A, B, and C. Okay? Now that's the front carbon. Now what about the back carbon? The back carbon, if you're standing here and you look out this way, the circle, by the way, represents the black carbon. The circle represents the black carbon. If you look this way, what do you see? Well, up and to your left, you're going to see a hydrogen. Up and to your right, you're going to see a hydrogen. Now, when you're drawing the back ones, those bonds go right here. Notice how they don't go into the circle, but they do touch it, because this circle represents the back carbon. Okay? And let's give these some letters. Let's call that A. Well, let's give it numbers. Call that 1, 2, and 3. All right. Now, this one, hydrogen 1, is right here. Number 1 should go there. Hydrogen 2, which is this one, is up and to the right. Let me put that up here so you don't confuse it with H2. And that will be 3. Up and to the left. Up and to the left. Okay? And that is how you draw a Newman projection of this particular molecule of ethane. Let me get my ugly mug out of the way here, guys. I'm sorry. There we go. Should leave myself over here, I guess. All right. Now, the conformations of ethane are eclipsed and staggered. Let me draw them for you. An eclipsed conformation drawn in a Newman projection looks something like this. And I'll explain it in a second. I can do better on that one. There we go. Now, let me draw the perspective drawing here. There you go. Let me use a different color. Use that one. Now this is eclipse, where if you were looking, say, from here, you're looking straight down this bond here, what you would be seeing is you'd be seeing, here we go, you'd be seeing this carbon and then this carbon behind it. So there's the carbon here in the front. This is the circle, is the carbon in the back. You'd see the hydrogen straight up, hydrogen down to the right, hydrogen down to the left, straight up, right, and then left. If you kept looking beyond, there's a purple hydrogen right here, which I've drawn right there. They're in front of each other. They're literally eclipsing each other, like when the moon and the sun overlap. One gets in front of the other. The moon obviously gets in front of the sun. That's an eclipsing effect. So this is an eclipsed conformation. Staggered. Now when I go through the conformations, I usually tend to put the front carbon, let me draw a little better than that for you guys. And I don't move it. I lock the front carbon in place. And what do I mean by that? I don't rotate it. I leave it exactly where it is. So notice how in this drawing and in this drawing, I left the front carbon essentially the same. Now the back carbon I am going to move. And what have I done? I rotated it this way. There you go. And that's a staggered conformation. Now, which one of these do you think is a higher energy conformation? It's probably this one, right? It's probably this one. Why? Because it's eclipsed. when these hydrogens are being forced to be basically one on top of the other, that's going to make the potential energy go up. And as it rotates through, the potential energy will go down until you get the perfect conformation, lowest energy conformation, and then it will slowly go back up as you keep rotating back into eclipsed. Remember, molecules aren't thinking. They don't know what's going on. They just know that they're looking for low energy. But when they found it, they don't know they found it, so they keep going. I'm just going to draw the eclipse conformation again, because it keeps rotating forward, keeps rotating through it. There you go. So it goes from eclipse to staggered, eclipse to staggered, eclipse to staggered, eclipse to staggered. It keeps doing this over and over again. It never stops. And those are the ethane conformations. Here's propane. Now imagine we're here, and we're going to look straight down this bond to the carbon in the back. How do we include that methyl group? It's real easy. It's real easy, guys. So there we go. Notice how I draw all my Newmans the same to start with. Hydrogen, hydrogen, hydrogen. We're here. Hydrogen there. Hydrogen down to the right. Hydrogen down to the left. Now if we're here and we look straight this way, we're going to see a hydrogen up and to the left and up and to the right. But then if we look straight down and look down in this direction, what do we see? We don't see a hydrogen, we see a CH3. Now you could draw it out. You could draw it out as an expanded formula, or you could just do what I do. Make your life easy. CH3. Okay? Now remember, this circle is the back carbon. The back carbon has these two hydrogens and a methyl CH3 straight on down. Okay? And that is the Newman projection of propane. And let's draw the conformations. The eclipse conformation. Again, notice I'm drawing the front one exactly the same as I always do. Nothing's different there. Why change it if it's not broken? And let me just put the CH3 right here. Hydrogen here and a hydrogen here. That's eclipsed. That's going to look something like this. There you go. There is the eclipse conformation. So this is the what's called perspective drawing, or side perspective. This is the Newman projection, and these are both eclipsed. Now again, I'm going to keep the front carbon exactly the same. I'm not going to change it. And all I'm going to do is rotate the back carbon this way. And that will put this CH3 here. The hydrogen will be here. That should be touching the line. And the hydrogen should be here. And that's staggered. Let me draw the staggered conformation. There you go. This is the staggered conformation. Let's continue. All I've done now is rotate this back carbon a little bit more this way. In case you wonder, there we go. More for completeness. There you go. And then we're back into eclipsed. Now, since the methyl group occupies more space than a hydrogen, The torsional strain will be 0.3 kcals per mole higher for propane than with ethane because it's bigger. Now, we haven't really talked about torsional strain. We are going to talk about it later. So just write the word down, and we'll come back to the term torsional strain. Torsional implies twisting or turning, so you can probably figure out what it means on your own. Butane's conformations. Now, butane has a few different conformations. It has more than the other ones. It has, well, let's just get after it. Let's just draw the conformations of butane. Oh, what am I doing? Forgive me, guys. I'm sorry about that. Those should have been CH3s. Silly me. Try that again. There we go. H. That's better. What was I drawing? Hopefully all you guys caught that. So there's one conformation of butane. Let's draw it. Let's change the color. Now here we have two large groups in an eclipse conformation. So the two large groups are eclipsed. This is called total eclipse. Total eclipse, or totally eclipsed, if you will. Okay, let me get my mug out of the, oops, that's not what I want to do. Let me get my ugly mug out of the way here. Let's put me over here today. All right, so now, what happens if we keep rotating? We take the back carbon and we rotate it this way. We're going to rotate the back carbon. I always rotate the back carbon. Sorry, I'm trying to make this as pretty as I can here. There we go. So there's the front carbon. It's staying exactly the same. I'm not changing anything about the front carbon. I'm only rotating the back one. So all I've done here is I've taken the back carbon and rotated it. And that means this will be and then this one will have there you go. The CH3 now has rotated forward a little bit, and this is called gauche. Gauche. When the two big groups are 60 degrees from each other, the two large groups, this is called gauche. Here we go. We're going to keep rotating the back carbon. We're going to keep the front carbon the same. Notice I always do it that way. I do the things that help me to do the right thing every time. No sense making life more complicated. So now the big group is now eclipsed with a hydrogen, or the large group is now eclipsed with a hydrogen. So that's called eclipse. It's no longer called total eclipsed because the, make sure I do this right. Yeah, okay. Oops. I'm supposed to use a different color here, aren't I? There you go. So this is called eclipsed. Eclipsed, where the big group is eclipsing with a smaller group, not the other big group. Okay, if it's eclipsing with the other big group, the two large groups are on top of each other or eclipsing. That's called total eclipse or totally eclipsed. Okay? Now, last one. I'm running out of room here, so I may have to do some fancy maneuvering here. Keep rotating. Keep rotating. But not the front carbon. The front carbon stays the same. Whatever you do, don't try rotating two carbons at once. You'll get confused. Just rotate the back carbon. And there you go. There's the other one. This is called anti. Anti. Where the large groups are 180 degrees from each other. Anti. This is known as anti. Okay? The large groups are 180 degrees from each other. Now let me try to find room to draw this here. I'm not sure where I'll find the room, but I'll do my best. I'll draw it down here. Carbon. Carbon. CH3. Hydrogen forward. Hydrogen backwards. And there you go. Anti. Where the two large groups are 180 degrees from each other. And here we are. Conformational analysis. Total eclipse, highest energy. Obviously, the two large groups are on top of each other, so that's going to be the highest energy. Let me just hammer out these Newman projections real fast. Gauche. Remember, Gauche is where the large groups are 60 degrees from each other. And then back to eclipse, but not totally eclipsed, right? Because totally eclipsed was the big groups on top of each other. Here the small groups and the big groups are eclipsing. Notice how the energy here for eclipsed is lower than total eclipsed by quite a bit. And then we're going to go into anti. Do better than that. There you go. And it keeps going. Remember, these molecules, they don't think. They just are reacting to energy, so they keep turning, trying to seek low energy. Now, what is causing this? Why is it such high energy in a total eclipse, for example? And it's because these two large groups are literally starting to bump into each other. They're starting to try to occupy the same space at the same time. Okay? And when they do that, something known as steric strain occurs. Steric strain is basically physical strain between two things. They try to interact in the same area, and they when they do that, their energy has to go up because now they're repelling each other, right? In order to be in that conformation, they have to be at high energy because they're literally repelling each other. Okay? And this kind of interference between two bulky groups is called steric strain, or people also refer to it as steric hindrance. Okay? Now imagine you have two groups that my two hands repel each other. And if I keep them far away, everything's okay. But when I try to bring them together, remember, my hand is negative, this hand is negative. I'm trying to bring two negative things in close proximity. That's obviously going to make the energy go up, okay, the potential energy. So these things are going to want to get there and then quickly get back out of it, all right, because the energy is too high because of electron repulsion. All right, so that is the end of this video. This for Newman projections and conformations. I know it's a little long. Sorry, couldn't really be helped. But I hope you have a good understanding of how to do it. I hope you can do it yourself. It's not that bad. It's a great way of representing molecules. Now, we're going to come back and do cycloalkanes here in the next video. But right now, I want to wish you all good luck and good chemistry. We'll see you soon.